So when negative them will come? Okay, so negative them. Okay, so I okay, negative them is negative them zeta is equal to what? Less than? Okay, less than 0. And k is greater than 467.2, meaning that it will goes to the RHP, right half plane. Okay, that is I add to the discussion. Right, so go to the next one, D. If 0 is added at -7, sketch the new root locus for the system. The new 0. So what happened if we add 0 to the root locus? 0 at -7. So this one I delete first. Okay. So this one is original. Okay. So if we add 0 here, okay, if we add 0 here, what will happen? Situ. Okay, what will happen if I add 0 over there? What is the plot? So I use the different color. Okay. Let's say I use a green color. Okay. So the root locus will become something like this. Okay, just a sketch. Okay, it goes here. And it goes here. Okay, goes here. And that one ended at 0. The other one ended at infinity. Okay, and this one maintain. Okay, this one maintain. Maintain as usual. Okay. Right. So the black one is the original before we added -7, and the green one is after we add 0 at -7. Right. So finish. Question 2. Okay. So question 2, please read for me. Azi Alia. Azi Alia, ada tak? Belum baca Azi.
Closed loop system in figure Q2A has the following open loop transfer function. The root locus of the system is given in figure Q2B. At any value of k, the system can be approximated as a second order system. Find the closed loop dominant poles if damping ratio zeta equal to 0.3. The system is required to have a peak time, Tp, 1 second, at the same damping ratio as in part A. Find the location of the new closed loop poles. Design a PD controller so that the required peak time is achieved.
Thank you very much. Okay, so again, you are being given root locus. But this is what you will get next week lah. Alright, so this is the open loop transfer function. Okay, and the root locus of the system is given. So at any value of k, then it is second order. So dia dah kata the system is second order. Okay, the system is second order. Okay, so this is the assumption. Find the closed loop dominant poles. Closed loop dominant poles at zeta 0.3. So if the given zeta is 0.3, is you're responsible to find the theta. Theta is cos 0.3. Calculator, please. Help me. Theta berapa? 72.5 degrees.
54.
72. Betul?
Tu je.
Okay, so 72.5. So kita pergi kat sini. Okay, so letak you punya protector center over here. Okay, so then saya ada kena ada pembaris juga, so saya pakai pen pakai pen. Oh, Allah tak cantik lah. So saya padam lah, tak cantik. So saya pakai gini je lah. Oh, tak boleh juga. Gini. Okay. Jadi. Okay. So this one is zeta 0.3. Okay. Which give you the theta. Theta kat sini. Okay. So the theta is theta 72.5 degrees. Okay. So the dominant closed loop kat sini kak. Okay. So what is the value? Anggaran. Tulis minus 0.8 plus J 2.4. Right. So itu adalah dominant pole dia. Jawapan dia. Okay. Then the system is required to have a peak time 1 second at the same damping ratio, which is zeta 0.3. Okay. Peak time dia 1 second. Find the location of the new closed loop poles. Okay. And then design a PD controller. Okay. Design a PD controller so that the required peak time is achieved. So from here, okay, so TP is given as 1 second. We know that TP is equal to pi divided by omega D. Okay. And then pi is equal to imaginary. Okay. So therefore, imaginary is sama dengan pi divided by 1. Kan? So pi divided by 1 is 3.14. So the J is 3.14. Okay. So J 3.14 meaning, okay, meaning that you have to find the real value. Okay. So what is the real value? Real dia. So there are two ways. One is by calculation, the other one is by graph. So 3.14 is somewhere here. So I use maybe I use a blueprint pula. Sini 3.14 kan. Okay. It will goes to this point. Okay. And then turun kat sini. Macam itu. Pakai rule of Case. Or you just simply calculate by using what do you call that? Pythagoras theorem. Okay. Theta sama 72.5. This one is 3.14. Okay. And this one is tak tahu. Okay, unknown. Right? So this one is zeta 0.3 line. Okay. So that's why real sama dengan zeta omega n. Okay. Which is sama dengan tangent 3.14 tangent 72.5. Okay. Which is lebih kurang zeta omega n lebih kurang 1 So that's why the real part is -1. Okay. So the new closed loop dominant poles are -1 plus minus J 3.14. Okay. That is the new one. Okay. And then design a PD controller so that the required design a PD controller so that the required peak time is achieved. Okay. PD controller. So kalau PD controller, you have to use what? You have to choose the ZC. Yeah? So you have to use the ZC. So in this case, we go to the show me. Right. So GPD. Okay. So GPD G cascaded. So it will come K S plus 10 S square plus 2S plus 2. Okay. So we have to find the new location for the Z. Okay. The new location for the Z is you can draw if you want. Okay. You can draw if you want. Then locate the what do you call that? The Z. Where to put the Z. So the important thing is the S new, the new Z must equal to the minus 180 degrees. So that's why S plus Z is the zeros minus angle because of the minus 10 poles. Then angle of the complex conjugate 1 plus J1 plus S plus 1 minus D1, okay, equal to minus 180 degrees, okay. Right, so from there, you insert the value of S, the new, S new, which is minus 1 plus J 3.14. You insert inside, okay, insert inside, and then it will be S plus Z, okay, is equal to 19.23 degrees. Okay, so that is the locations of the zeros, okay, that we introduced in the PD controller. Then it locates over here, okay. This is your ZC, okay. So this is your 3.14, okay. And this is your dominant pole, minus 1 plus G 3.14. Okay. And this is your minus 1 real part, okay. And this distance is unknown. We have to find the distance, okay. So this is 90 degrees, right? And the angle here is 19.23 degrees. So similarly, you can calculate the value of x, okay. X equal to 3.14 divided by tangent 19.23 degrees, which is equal to 9. Okay, x to 9. Jadi ZC will be minus 1 minus 9. So it will be minus 1 minus 9 equal to minus 10. X2 is just a distance. Okay, so you don't assume 9 to as the minus 9. It's wrong. So distance the between that two particular points, so it will become minus 10. Okay, so ZC will become minus 10. So GPD ZC is 10, so that's why GPD is S plus 10. Okay, S plus 10. And then you calculate the gain K at that point. Okay, calculate gain K at minus 1 plus J 3.14. Okay, so how to calculate it? So you use the gain criteria. Okay, so gain criteria is, what is gain criteria? Okay, okay, your S plus 1 plus J1, S plus 1 minus J1. Okay, so insert the value of S here inside. Okay, then simplify, then you will get K is equal to 8.8. Okay, so therefore GPD is equal to KP plus KD. Okay, GPD is equal to 8.8 S. Okay, so GPD, KD, S, KP over KD. Okay, KD is equal to 8.8 and KP is equal to 8.8 multiplied by 10. So it will become 88. This KP and KD will be inserted into the controller. In reality, if a digital controller, so you insert this value 8.8 as KD and 88 as KP. Okay, so this is what I call a PD controller design that satisfied the requirement of the peak time 1 second. Okay, right. Any question? Ada soalan?
Sir,
Ya.
yang angle S plus 7 tu, yang 19.23 tu dapat mana?
19.23. 19.23. Oh, dia dekat sini. (19.23) adalah daripada sini. Angle criteria. Angle criteria. S plus Z. Z we don't know. Then we calculate the angle. S plus 10, S plus 1 plus J1, S plus 1 minus J1. S ni, this S, you insert this value. Minus 1 plus J 3.14. You insert here, then you insert here. Okay? Then you simplify. So you kena pakai apa ni? Kena pakai tangent ni. Kena pakai tangent. Saya ringkaskan sebab nak jimat masa. So yang ini nanti, okay. So dia akan jadi sini. S plus Z, okay. Minus, okay. 9 plus J 3.14, okay. Plus J 4.14 plus J 2.14 equal to minus 180 degrees. So that's why we dapat SZ sama dengan 19.23 degrees. Okay. Kena masukkan nilai itu dulu. Insert the value. Okay, you insert the value here. Dan cari dia punya angle. Guna tangent lah. Up tangent. Dan samakan dengan minus 180 darjah.
Okay.
Okay. So masa tinggal less than a minute. So we stop here. Then we continue again after 15 minutes. Boleh? Hello? Boleh
Boleh sir, boleh sir.
Okay. Untuk soalan yang kedua, set kedua. Thank you very much.